topic for today is 1.2 functions. Key vocabulary, relation. A relation is a mapping or pairing of input values with output values. A function is a relation for which each input has exactly one output. Domain is the set of inputs, generally the X, and the range is the set of outputs generally Y. Okay, let's look at example 1. We have a set with 3 ordered pairs. We want to first talk about what is the domain of this set. The domain would be our X values. 1, -5, and 7. The range would be 3, 3, 4. Now, because 3 is repeated, we only need to write it down once. Next question, is S a function? Well, what we begin to do is we want to do a little mapping. So we map our domain to our range. Okay, we're going to map our domain to our range. So 1 maps to 3, -5 maps to 4, and 7 maps to 3. Since each input maps to only one output, this makes it a function. All right, let's look at another example. Example 2, we have a different set here. What is the domain of S? The domain of S would be 2, 5. Now, I do not have to write down 2 again because it is already listed. Our range would be -3. I do not have to write down -3 again, and then 3. So when we map it, our domain and our range, 2 maps to -3, 5 maps to -3, so we're still okay. But then when 2 maps to 3, we have one input that maps to 2 outputs. So it is not a function. It is a relation, but it is not a function. Example 3, which of the following equations represents y as a function of x? It's a function of x. What that means is that when I put in a value for x, I get out one value for y. So what I want to do is solve for y. So when I solve this for y, I'm going to subtract a 2x squared and 1 from both sides. So I get a negative 2x squared minus 1. Now for every value of x that I put in, I'm going to get out one value for y. So each value of x yields one value for y. So it is a function. Now let's take a look at b. When I solve this for y, I'm going to subtract an x and add a 6 to both sides to start. And then to solve for y, I take the square root of both sides, but when I do that, I end up to plus or minus, because I had to take the square root of both sides. Now, for every value of x that I put in, I now have two values of y. So each value of x in this one yields two values for y. So it is not a function. Example 4. Basically, what we're looking at is evaluating here in example 4. We're going to be evaluating functions. Which is just a fancy word for saying substitution. In this problem right here, that now becomes the value for g. And what I'm saying is g is going to equal 2. So if I substitute it in, be careful of that term. That's a negative 1 times 2 squared minus 5 times 2 plus 3, and negative 4 minus 10 plus 3 will yield negative 14 plus 3, a negative 11. So P of 2 equal to negative 11. I'm going to do the same thing with negative 2. My g value now becomes negative 2. So I'm going to substitute it in. Negative 1 times a negative 2 squared minus 5 times negative 2 plus 3. Negative 4 again, because it's negative 2 squared is 4 times negative 1. Negative 4 plus 10 plus 3 gives me 9. So P of negative 2 equals 9. Now I could do more than just substitute numbers in. I could go ahead and substitute variables, or as in D, we could substitute an entire expression. So let's start with P of x. This one's very basic. Negative x squared minus 5x plus 3. Final answer for that one. D is a lot more entailed, because I'm going to have to substitute the entire expression of x plus 2 into the equation. So I'm going to say it's a negative x plus 2 squared minus 5 times x plus 2 plus 3. Now remember, when I have a binomial squared and I I have a binomial squared, like that, it's not a distributive property. A binomial squared means x plus 2 times x plus 2. I'm going to equal here, negative, and this is, multiply that out, I'm going to get x squared plus 2x plus 2x plus 4. Squared plus 4x plus 4. I can distribute here a negative 5. I need to distribute the negative Now I'm going to combine my like terms. Negative x squared, negative 4x, negative 5x, negative 9x, negative 4, negative 10, plus 3 will yield a negative 11. So P of x plus 2 is equal to the trinomial. Example 5. What is the domain? Remember from Algebra 2 we talked about domain. What values of x can I put into this function? In this case, I can put in any value of x that I want, and it'll still be a defined function. So my domain is all real numbers. That symbol, again, is a symbol for all real numbers. Again, why is it all real numbers? Because any of the value of x yields a value for y, or gives me a value for y. However, there are functions in which the domain is not all real numbers. They have limits to them. Okay? They don't all work that way. We're going to look here at the implied domain of a function to be the set of all x such that the corresponding y is a real number, at least for a while. We're only going to consider these three situations for today's purposes. Situation 1, polynomials. Okay? Again, a polynomial, the domain is all real numbers. So if I'm looking at a polynomial here, yes, it's an x squared, it's a quadratic, it's a parabola, but it's still a polynomial. It's an addition of a bunch of monomials, addition, subtraction. So my domain will be all real numbers. It doesn't matter what degree it is. This is a degree 2, this is a degree 5. It could be a degree 4. The domain is still all real numbers. So that's our first situation, is polynomials. In our second one, we're looking at fractions, or rational expressions. Okay? They have variables in the denominator. What we can't have is a number in the domain that makes the denominator 0. Okay, so the denominator, since we cannot divide by 0, can't divide by 0, therefore the denominator cannot be 0. So in this case, what we'll write, we'll say the domain is all real numbers except x cannot equal 2. Because if I plug in 2 or substitute in 2, 2 minus x minus 2 cannot equal 0. So x cannot equal 2. Does not matter what the numerator is. So in the second example, the numerator does not even play into what the domain definition is. We know that x plus 8 cannot equal 0, so x cannot equal negative 8. So our domain will be all real numbers second situation. Last situation we're going to look at for now are radicals. If the index is even, that's kind of key there. This is the index. In that case, we have an even index. Then the radicand must be non-negative. In other words, it could be 0 or positive. So what I say is x plus 7 is greater than or equal to 0. So I'm going to say my domain then, x has to be greater than or equal to negative 7. Again, I have an even index. So now I have to say that my radicand, the number under the radical or the expression, has to be greater than or equal to 0. Okay, when I divide by a negative, remember what you do with the sign. We divide by a negative of an inequality. Negative divided by a negative is a positive. So my domain has to be x is less than or equal to 4/3. What happens when the index is odd? Can I take the cube root of a negative number? Say, for example, can I take the cube root of negative 8? Yes, it's negative 2. Can I take the cube root of a positive 8? Yes, it's positive 2. So I can put in any value of x and it'll yield a value out. So when the index is odd, my domain will be all real numbers.